In the last several videos, we began to explore ways to go about determining chemical structures for organic molecules, which is a key tool when we are dealing with things like conducting chemical reactions. We need to be able to confirm that the theoretical molecule we synthesized is in actuality what we created. This strategy or ability to solve chemical structures is also really valuable in fields such as medicine. For example, if it's hypothesized that a patient has a particular disease due to some chemical that is being produced within the body, we need to be able to determine what the structure of that particular molecule is. And so in the last module, what we focused on was IR, which allows us to determine what functional groups are present within a molecule, and mass spectrometry, which we generally use to determine the molecular formula of a molecule. Neither of those techniques, mass spectrometry or IR, allow us to stitch together the complete chemical structure. In other words, neither of those methods allow us to determine all of the chemical bonds within a molecule, so we can't typically, with mass spectrometry or IR, assign complete chemical structures. So to fill in that information and enable us to determine complete chemical structures, what is widely applied is a technique called nuclear magnetic resonance spectroscopy, or NMR for short. So I'm going to spell that out as nuclear, and nuclear here refers to the nucleus of the atom. Magnetic, and we'll get into what we mean by magnetic here in just a moment, as well as the resonance feature of this. And when we say resonance here, I will straight away warn you that the term resonance does not refer to resonance like we learned about previously in Organic 1, where we would be using electron pushing arrows to show that a particular molecule could have different arrangements of electrons within that structure. Instead, the term resonance here will take on a different meaning. So let's get into what we mean by nuclear magnetic resonance and what information that can provide about a molecule. You may be wondering, as we take a look at this title slide, why I have a bunch of child's tops here on the slide. And the reason is that when we think of the nucleus of an atom, a feature of some nuclei is that they will have multiple spin states. So much like a child's top, certain nuclei of atoms can rotate around. Much like if we envision my laser pointer in the upper right-hand corner with that green top is showing that it's rotating in a clockwise direction here. Similarly, atomic nuclei can also do that. So what enables atomic nuclei to have multiple spin states, and how can we use those multiple spin states in order to determine information about the structures of molecules? Let's dive into that. So we use the term spin states to refer to the fact that some nuclei can rotate differently, clockwise versus counterclockwise, for example, about the axis of that nucleus. In order for an atomic nucleus to have multiple spin states, it must have either an odd atomic number or an odd mass number. So in order for there to be multiple spin states, which are a prerequisite for this phenomenon called nuclear magnetic resonance, multiple spin states will exist for nuclei that have either an odd atomic number, where remember that the atomic number refers to the number of protons within that particular atom. So if you look at your periodic table, for example, the atomic number of hydrogen is 1, the atomic number of carbon is 6, indicating that hydrogen has 1 proton, carbon has 6 protons. And by the way, there is a periodic table available too. If you go under files, the periodic table that we will be using in the class is shown there for you. Alternatively, or additionally to having an odd atomic number, another way to result in a nucleus that can have multiple spin states is that that nucleus has an odd mass number, remember that mass number refers to the sum of the number of protons plus the number of neutrons. So if the mass number of a particular atom is odd and or the atomic number of that atom is odd, the molecule will exist in multiple spin states. Those multiple spin states will create what we refer to as a nuclear magnetic moment. A nuclear magnetic moment is just a tiny magnetic field that surrounds that particular nucleus. And that is what we start to look at when we are using NMR spectroscopy to gather information about molecular structures. So molecules with multiple spins, or nuclei specifically, the nucleus of individual atoms with multiple spins, and specifically multiple spin states, will have associated with that a specific nuclear magnetic moment. When we say a nuclear magnetic moment, what we mean by that is a magnetic field that is associated with that nucleus. So each individual nucleus within a molecule that is present in multiple spin states, meaning each nucleus that has an odd atomic number or an odd mass number, is going to have an associated magnetic field surrounding it. And that associated magnetic field is what we will be relying upon in order to collect an NMR spectrum and in order to deduce specific features of the structure of that molecule as a whole. So when we are thinking about what atoms are we able to determine an NMR spectrum for, in other words, what particular atoms meet this criteria up here of having an odd atomic number or an odd mass number, we can look at a variety of atoms within the periodic table, and we should be able to deduce what atoms, nuclei, will be NMR active versus which ones will not be detectable by NMR. So in order for a nucleus to be detectable by NMR, it needs to meet one of these two criteria: odd atomic number, odd mass number. So we can ask the question of, can we detect by NMR? And the specific scenarios we'll focus on here are atoms that are commonly found within organic molecules. So when we think about organic molecules, generally the most abundant atom within typical organic molecules is hydrogens. So if we think about a hydrogen, the typical isotope of hydrogen is hydrogen 1, which I'll put as 1H. That indicates that hydrogen has 1 proton and no neutrons. Would that be detectable by NMR? Does it have multiple spin states, in other words? The answer is yes, it has multiple spin states because with 1 proton, it definitely has an odd atomic number. And so it meets the criteria for being NMR active. And so I'm going to put a check mark next to that to indicate that yes, we can detect that by NMR. So what about instead, the most common isotope of carbon is carbon-12. That would be another useful atom to be able to detect by NMR. So can we detect that? In the case of carbon-12, carbon-12 has 6 protons. If we look at the periodic table, its atomic number is 6. And since the mass number of that is 12, that means it has 6 neutrons and mass number is 12. So can we detect carbon-12 by NMR? The answer to that question is absolutely not. So I'm going to put a red X next to that. The reason is the atomic number of carbon-12 is 6 because carbon is the 6th atom in the periodic table. It has an atomic number of 6. And the mass number here is indicated by the isotope number here, carbon-12, indicating that the mass number is also even. So carbon-12 is absolutely invisible by NMR because it doesn't exist in these multiple spin states that allow it to create its associated magnetic moment. So how do we go about detecting carbons in NMR experiments? Because carbon is a really common atom, so it seems it would be really useful to be able to detect that to determine the structures of organic molecules. Well, the workaround for this is that carbon-13 while present only as approximately 1% of the natural abundance of carbon that is out there, is detectable by NMR. And so by random chance, when exploring a molecule that you have synthesized, 1% or so of the carbon atoms will be carbon-13 that can be detected by NMR. And so the reason why carbon-13 is detectable by NMR is it still has 6 protons, much like carbon-12, identical to carbon-12, but the mass number here is 13 because it has an extra neutron. And so, therefore, with that odd mass number, we are indeed able to detect carbon-13 by NMR. And so hence, 2 very common types of NMR experiments are what we refer to as proton NMR experiments, or proton NMR spectra are the data that would result from conducting a proton NMR experiment. So we call that a 1H NMR spectrum. Another common NMR spectrum that we collect is a carbon-13 NMR spectrum. The principles of these 2 types of NMR, carbon-13 and proton NMR, are very analogous. And so for purposes of organic chemistry 2, we are going to focus our discussions primarily on proton NMR, and we will be using proton NMR as the main tool that we use to evaluate the structures of organic molecules. So now that we have established that spin states are essential for the creation of nuclear magnetic moments around particular nuclei, such as protons and carbon-13, let's take a closer look at the steps of an NMR experiment. In other words, how are we going to collect information about the nuclear magnetic moment, and how will that ultimately translate into information about the structure of an organic molecule? So what we see here is a typical NMR instrument, and you can find the handout with this image on it if you go to the Chapter 13 module and take a look there. So you may want to have this information handy. So in order to collect an NMR spectrum for a molecule, what happens is that the molecule is first solubilized in a solvent and placed into an NMR tube. The NMR tube looks something like this. It's similar to the size of a pencil. So you're looking at the lower left-hand corner here. And in that NMR tube, the compound of interest is solubilized in a deuterated solvent. What do we mean when we say a deuterated solvent? A deuterated solvent is one that, rather than having standard common protons in it, instead it has deuterium. So it has 2H, hydrogen 2, rather than our standard protons in the solvent. So for example, if the solvent is chloroform, which is a common solvent used for NMR, rather than it being CHCl3, which is the formula for normal chloroform, instead it would be listed as CdCl3, where the D here stands for deuterium. And this is important because deuterium, 2H, is invisible to the NMR spectra, to the NMR instrument. So in order for us to be able to focus on and detect and evaluate the compound of interest, the compound of interest is solubilized in a deuterated solvent, and that deuterated solvent is invisible. So what we detect when we evaluate the material in this NMR tube is just the compound of interest, not the solvent that we have solubilized it in. If we solubilized our compound accidentally in normal solvent, we would see a gigantic solvent signal because the solvent would contain regular old protons, which are detectable by NMR because they have that odd atomic number. But in the case of deuterium, deuterium has an even atomic number, and so it is going to be invisible by NMR. So the sample is placed into this NMR tube. The NMR tube is inserted into the instrument. So the instrument is this cylinder object here, about as tall as I am, so something like 5'5" or 5'10". The NMR tube goes into the cylinder following my laser pointer down and ends up right here where I'm circling with my laser pointer. That is where the NMR tube ends up. And you can see that there are magnetic coils that are surrounding that NMR tube that is placed into the instrument, where the NMR tube you could think of as that red line that I have drawn within the instrument. So what's happening here is that the sample is placed into a magnetic field. So we're going to list as our steps of NMR. Here is step 1, is that the sample is placed into a magnetic field. And that's what we're showing when we showed that NMR tube being inserted into the instrument surrounded by those magnetic coils. What is going to happen here is once that sample is placed into the magnetic field, the nuclear spins. Remember how the nucleus of these certain atoms are going to spin like a top. Those nuclear spins are going to align with the magnetic field that has been applied. So in other words, spins from a particular proton are going to synchronize with one another. So the nuclear spins, the spinning of those NMR active nuclei, are going to align, meaning go the same direction as the magnetic field. And the magnetic field is being applied by the instrument. So then what happens next is that the nucleus, once it is aligned with that applied magnetic field, is going to be exposed to a range of frequencies of electromagnetic radiation. And what will happen is that when a very specific frequency is reached, energy will be absorbed by the nucleus and its nuclear spin will flip, for example, from positive 1/2 to negative 1/2. And resonance is what we refer to as that flipping of the nuclear spin state from positive 1/2 to negative 1/2, for example. The resonance frequency will give a signal that is readily detectable. And that signal frequency will depend upon exactly what environment each individual hydrogen is present in. In other words, what we mean when we say the environment of that hydrogen is what atoms are nearby. So if the atom is nearby an oxygen, it is going to have a different resonance frequency than if that hydrogen atom is near a carbon. So let's go ahead and write down part 2 here in words on paper. And that is that when the nucleus is exposed to the electromagnetic radiation, at a certain frequency, energy will be absorbed and the nuclear spin flips. For example, from positive to negative. And what we describe that flipping of spin states as is resonance. So resonance is going to be that flipping of the spin state. And that specific resonance frequency, because we said that this radiation has to be at a certain frequency for energy to be absorbed and the nuclear spin to flip, we refer to that particular frequency as the resonance frequency, and that's going to give a signal that's detectable. So we can say the resonance frequency gives a detectable signal within the NMR spectrum. So different protons within a molecule will have different resonance frequencies. And therefore, the different protons having different resonance frequencies can be differentiated from one another. So what we are going to look at in the next video is how does the exact environment of a proton determine what frequency it is going to absorb this electromagnetic radiation at to undergo these nuclear spin flips, and how can we tie that information to the structure of the molecule.